Hey everyone, welcome back to my channel. Today I'm going to talk about the benefits of high-resolution ESP data for well testing. This is a little bit of a long paper, but I'm sure that I'll condense it down to 10 to 15 minutes of material as best as I can. Before we get to the content, please be sure to like this video, subscribe so you can get more content in oil and gas and professional development topics, and please be sure to comment on the video so I can incorporate your feedback into future videos. Be sure to hit that notification bell when you subscribe, as I upload every Friday and every Sunday. Every Friday is a professional development topic, and every Sunday is a technical review, such as this video. Well, let's get on with the content. Hi everyone, as I mentioned before, today I'm going to talk about ESP real-time data. Enables well testing with high frequency, high resolution, and high repeatability in an unconventional well. This is written by Lawrence Camilleri, M. L. Guindy, and A. Rusakov from Schlumberger. I bolded the objective to get an idea of what this paper is about, and I've broken down this paper as best as I can, as this is a very lengthy paper discussing the details of high-resolution ESP data and the calibration process. This was to investigate a novel method for obtaining very high-frequency measurements using ESP data from both downhole permanent gauge and the surface variable speed drive, or VSD, thus leveraging the standard ESP installation to obtain the critical reservoir information. High-frequency measurement is necessary to obtain a representative profile of rate and pressure versus time, which requires a dedicated multi-phase flow meter or test separator on each well, and the algorithms use real-time data. The liquid flow rate calculation is based on principle that the power absorbed by the pump is equal to that generated by the motor, which can then be resolved for rate. Here's the table of information for the two wells, or two ESPs for the case study. This is the measured parameter that we're going to be using for the study. So your pump intake pressure, your ESP discharge pressure, your tubing head pressure, your VSD output, your voltage at VSD output, and your frequency. And your data source is going to be your downhole gauge, your wellhead gauge, and your VSD controller. And then here's some information for the first and the second ESP when looking at the table on the left over here. To point out, the real-time data frequency is once every 10 minutes because that's the data that we typically get from our SCADA system. And here's the extension of the table 2, where you have the frequency of the reported test separator data, your pump, your gas handler and separator, your motor, your depth of your gauge, and your length of your tubing, as well as your tubing size. So this is for an unconventional shale oil well. Here's some of the data that's shown here. For the first ESP, you have motor temperature, current, and pump discharge pressure that shows increased oscillations. If you notice over here, especially with high GLRs, that's when you have high GLRs and high tubing pressure increases as the pump intake pressure drops. So you have your pump intake pressure dropping and you get these oscillations. Then this is the second ESP, where you have high GLR and a prolonged shutdown illustrates that there is a reduced GLR in the subsequent startup, suggesting the GOR is equal to the solution GOR of this well. So with the low GLR, with the reduced GLR, that the GOR is equal to the solution GOR. I'll talk about some of the challenges for virtual flow metering specific to shale oil wells. There's a large turndown and absolute value of liquid rates to be measured, so there's large ranges of fluid rates. There's increasing GLRs affecting flow rate calculations, and the paper refers to GLR when conducting calculations as the downhole GLR at the pump intake. So it's not measured at the surface, these are all downhole measurements. There's free gas at the pump that causes degradation of pump performance, and production tubing flow regime changes with time, and that changing holdup affects water cut calculations. Startups are another important phenomenon to take into account because a finite amount of time is required to overcome the phase segregation and unloading of fluid in the casing prior to 100% from the reservoir. I'll talk a little bit about the liquid calculation methodology, and it's really through the power equation. So that provides a unique solution across the full flow range of the pump curve irrespective of the pump type, not the case for traditional pump rate calculation method. There's a unique solution for any measured dP power over power, meaning that this can be calculated independent of the pump flow curves used traditionally. The use of the analytical equation derived from the first principles, as opposed to a correlation or neural networks, ensured that any change in measured data was translated to change in the flow rate. And the power equation relies on the fact that the measured current varies linearly as a function of flow rate. And the power equation is independent to the fluid-specific gravity because there are some unknowns due to changing water cut and GLRs in the pump and the tubing, which is why specific gravity can be an unknown when you do the traditional calculation. I'll talk about the value of uncalibrated trends, and there's some justification behind it, but there's going to be some further justification of calibration. It captures the change in flow rate, but not the correct absolute value, as calibration is required to remove measurement and modeling errors. And there's two types of the uncalibrated trends that we're going to compare. You could have instantaneous flow rate and the lagging 24-hour rolling average. The rolling averages have the same trends as the test separator measurements, but the rolling averages could be misleading compared to instantaneous rates. These instantaneous rates enable improved differentiation between the phase segregation effects and reservoir production, and that's with respect to water cut. And that allows the identification of the change in well performance to increase drawdown when plotting inverse productivity versus time. So the change in y-intercept is key to optimizing the ESP frequency and choke settings, and it's not the absolute value of the liquid flow rate. Now I'll talk about the calibrated liquid flow rate trends. Here's some of the reasons: because there's some error sources from the following. There's some gauge pressure measurements, which are small errors. There's surface electrical measurements, and if it's not calibrated in the field using a handheld meter, then there's some bias. Then from the pump efficiency curve, there's some errors, and there are couples that should be taken into account. The actual pump installed has a slightly different efficiency curve, although within the tolerances of API RP11S2, and there is potential degradation of the efficiency curve due to wear, gas, or viscosity. There are potential errors in the calculation of motor-generated power, which relies on modeling of the motor to obtain the motor power factor and efficiency. So here's the traditional process where you have the flow rate calculation, or the factor calculation, which is your rate of your downhole average times your rate of your surface, and you use your water cut times your formation volume factor. Surface rates and formation volume factors aren't always available, so the conditions should be met for the traditional process to be true. So the pump has not suffered any wear, no pump performance degradation due to gas, and no pump degradation due to viscosity. So here's the novel method, which is known as the PHI method, and the workflow is detailed quite a bit more in a 2015 paper that is written by Mr. Camilleri. So there's the differential pressure over power of the actual over differential pressure of the power of the reference, and then you have this index, or this ratio. So this is the pump absorbed power that's calculated using the same method employed for liquid rate calculation, which is a function of voltage, current, and frequency real-time measurements. And the dP power reference is obtained from pump curves using factory test points. Here's the calibration that was done for the first ESP, where you had the calibration period for the first 82 days, and you had your PHI of about 1. And then you have severe surging when you have different flow regimes coming up. Here's the calibration period for the second ESP when oscillations and rising GLRs started happening. Here are the applications for the PHI. You can do the monitoring and pump operating point. You can monitor and optimize the motor current. You can use the PHI as a diagnostic tool and a recalibration flag, so you need to recalibrate your ESP downhole data. You can use the single well inflow surveillance, so you could compare RTA analyses and diagnostic plots using the downhole rate data that is calibrated using this PHI method. And there's other workflow applications such as early drawdown management, permanent versus occasional surface well testing facilities, reservoir surveillance and long-term drawdown management, power optimization, and ESP run life management. Now the paper goes more into detail in calibrating using the water cut as well and improving the accuracy of the water cut, but I didn't go over it in this presentation because I wanted to focus more on the liquid rate calculations and how the benefits of PHI or using this equation or this relationship from the power equation can benefit unconventional wells. I want to thank everybody for taking the time to listen to this presentation. And before I end this, please be sure to like this video, subscribe for more content in oil and gas and professional development topics, and please be sure to comment on the video so I can incorporate your feedback into future videos. You can follow me on LinkedIn, Twitter, Facebook, and Instagram. YogashriPradhan is the consistent handle for all of those platforms that I mentioned to you. Once again, thank you so much for your time, and I'll see you in the next video.